So let's look at one more problem where we're trying to find the distinct equivalence classes. So let's look at, let R be the equivalence relation defined on Z by A relates to B if 2A plus B is congruent to 0 mod 3. And I want you to find the distinct equivalence classes of R. So the first thing you're going to do is you're going to take an integer and find its equivalence class. So let's start like we've done all of the other ones. Let's begin by finding the equivalence class of 0. So this is all the elements in Z where x is related to 0. Well, this corresponds to all the elements x and z where 2x is congruent to 0 mod 3. This means that I'm looking for the elements x and z where 3 divides 2x. So what elements are in here? 0 plus or minus 3, because then you'll get plus or minus 6, right? And so forth. X has to be a multiple of 3. Again, this can't be all of my equivalence classes because there are integers that are not in this set. So take an integer that's not in that set, like 1, and find its equivalence class. Okay, so I'm looking for all the elements x and z where 2x plus 1 is equivalent to 0 mod 3. Well, this is the same thing as saying I'm looking for all the integers where 3 divides 2x plus 1. So what would be elements in this set? If x is 1, 3 will divide 2x plus 1. If x is 4, 3 will divide 9. If x is 7, 3 divides 15. And you can even go downwards, negative numbers. If I plug in negative 2 for x, 3 will divide negative 3, negative 5, and so forth. Okay. Again, this can't be I can't have just 2 equivalence classes because there are elements that are not in these 2 sets here. So if I look for a number that's not in these 2 sets, for example, 2 is not in those 2 sets, so I can find the equivalence class of 2. Okay, the x and z where x is related to 2, x and z where 2x plus 2 is congruent to 0 mod 3. And you can say that this is x and z where 3 divides 2x plus 2. So if I write out the elements in this set, in this equivalence class, you would have x is 1, or sorry, not 1, x is 2. Yep, because then 3 will divide 6. X could be 5 because 3 would divide 12. X could be 8. 3 divides 18. And then you go down, x could be negative 1 because 3 would divide 0. X could be negative 4. So if you look at these equivalence classes, now I've got every integer appearing in one of these 3 sets here that I've put an arrow next to. If you compare these with the equivalence classes that we found in the last video, you'll see that these are the same. So I'll note that these were the same equivalence classes as the relation given by A relates to B if A is congruent to B mod 3. And so in some ways, because we have the same equivalence classes, we could think of these relations as being kind of like the same. They're not described the same, but the same elements are related to each other. So what you could prove is that if A is congruent to B mod 3, this is true if and only if 2A plus B is congruent to 0 mod 3. So it turns out that 2 elements are related in one relation, then they would have to be related in the other relation as well. So in some way you can think of these as being like the same relation. They're just not described in the same way, but they give you the same equivalence classes.